All right, so let's continue. This is the last discussion related to layout. And if you recall, in the last lecture, we were looking at design, and we said one way of carrying out design is you start from the specs, and you have to produce the final design, which is in the form of a layout. And to do the layout and to do other things, you require technology information. And you can integrate into the design. Obviously, you have to integrate and you produce a design which is technology specific, is for a 180 nanometer technology or for a 90 nanometer technology, is technology specific. And as you move to a different technology, a year and a half or 2 years down the line, if you follow this particular methodology, you may have to redo the whole thing again, because the technology information is deeply integrated into the design itself. The other way of doing it is you take specs and you design it at a higher abstraction level. So you have an intermediate form, which is technology independent form, right? So it's a technology independent form. So it's going to remain the same as technology changes. And as the technology changes, what you do is you take this intermediate form, you add the technology information to it, and you produce the final design. So this is likely to be more efficient because you're able to reuse a part of your design effort. Once you do this particular design effort, then you can reuse it again and again. And in that context, we were seeing that lambda rules are an example of technology independent representation. And we saw this example, but we said also that they have a disadvantage. Lambda rules, maybe they represent the worst case rules. And we were looking at this hypothetical example that in technology 1, let's say 1 micron technology, they have certain rules, L1, L2, L3. These are all minimum dimensions. And for technology 0.5 micron, let's say the dimensions are 0.5, 3, and 2. If you want to construct a set of design rules such that the design is valid for this as well as this, then we said that in terms of lambda, if I take lambda 0.5, so these are the rules, and lambda is 0.25, then these become the rules. So if you want to construct a technology independent set of rules, then you take the worst case. So in this case, you take a rule for L1, which is 2 lambda. For L2, you take 20. Minimum dimension is 20 lambda. For L3, you take 8 lambda here. So you construct a set of worst case rules. And with those worst case rules, of course, the design would work. The design would work for both 1 micron as well as 0.5 micron. But we also said that what this approach does is that it's not fully taking advantage of the rules. For example, if we have a rule called 20 lambda, a new technology allows us 12 lambda. So we're not taking advantage of the fact that this dimension is only 12 lambda. We're using a very conservative set of rules, 20 lambda. Conservative, why? Because it has to be valid for all generations. So, you sort of construct a set of very conservative worst case scenario rules. And then those rules will hold for all generations of technology. So, yes, we get a technology independent representation in terms of lambda, but we have a price to pay. A price in terms of area, and depending on the dimensions, the capacitances and everything change. And so you have a price to pay in terms of power and price in terms of performance, delays and power and all of that. All right, so is there so benefits of scaling to some extent lost here. Is there another way that we can do that? So this is what we are looking for. That we are looking for specifically in the context of layout now. You can think of this kind of a, methodology at various levels that you want a technology independent intermediate design. So in the context of layout, I want an intermediate design, in the context of layout, intermediate layout information, which is technology independent, right? So what kind of that representation would be? And I want to take advantage of the actual rules also, right? So what we want is, let's say I have a NAND gate and I want to take a NAND gate or a CMOS inverter. Okay, I want to take a CMOS inverter and I want to construct this layout. And layout in an intermediate form. The final layout is here. In an intermediate form, I want to construct a layout. And then the technology information, which in the context of layout is what? All the design rules. All the design rules in actual microns. So that technology information. In the next design step, I will add the technology information to my intermediate design and get the final layout. Right? So this is what we are looking for. So what kind of an intermediate design stage is it which has some information about the layout, but is technology independent? Now, if you think about what we are trying to do, you would note that what is the technology information? It is the sizes, different dimensions. So if I have a technology independent representation, that technology independent representation cannot have any information about the dimensions. Because where are the dimensions information coming from? From the design rules, which are specific to a technology. So if you want a technology independent representation, then that independent representation would also have no information about the size. Then what are we talking about? A layout. A layout without size information? Layout is all about sizes, geometrical drawings and all that. So what we are saying is that what we are looking for is a symbolic layout. Symbolic layout which doesn't have any information about the size, actual sizes here, but still has relevant information. So what we are talking about is what we call as a stick layout. As an example, stick layout. So what do I mean by that? So it has some information, valuable information, but doesn't have information about the sizes here. So this is the layout that we had done for a CMOS inverter. Now, stick layout for this would be here. Stick layout for this would be this particular layout here. Now, does it carry any information? So you can see what this is doing here. This big rectangle that you see here, which is supposed to be the PMOS, and there has to be a P plus diffusion. So this is the stick here. Because I don't have any information about the size. So I have a stick here, one line here, which represents the P plus diffusion here. And there's a poly here, which intersects with the poly is here. So that's where you get a transistor. Then this poly runs here, and poly runs like this here. And then comes here, and there is an N plus diffusion area, N plus area here. So this is my N plus area here. And this intersects, so I get a transistor here. And then there is a contact here, so I use a cross to indicate a contact, and use a cross to indicate contact. And then, we can use different, I've used here colors and a little bit of, you can use various ones. I mean, you can even write on top M1, M2, metal 1, N plus and all that. So this is where I take the output. And this is where I make a contact again, and the contact is on metal 1. Final input is on metal 1, so I get here. Plus, I have a contact here, so there is the VDD here, and there is a ground here. I didn't indicate the body contact. So body contact also one could indicate by, let's say, putting another cross here or another line, which is a green line here, and putting a contact there. And similarly for the other one. So this is it does carry some information about the structure, because note that once I create something of this kind, how do you arrive at this one? What do you have to do? You have to add the size information. And where do I get the size information? All the rules that are there. Plus, I also have what is the size of my MOSFET. W by L of the MOSFET and W by L of this particular MOSFET is known. And so the size of the MOSFET information I have, and all the rules that I have. So it's actually a sort of a very routine or a mechanical kind of a thing to, once you have drawn something like this, then each one of them you have to expand into a rectangle, and once you know all the rules, you can expand them and construct this particular one. So this does carry information. For example, I could do a layout of this particular inverter in a different manner here. So this is one way of doing it. Another possibility is I could have done it like this. I can do the layout in this particular manner here, note. I could run this here, note the poly is here, and then ground. And you can see that there are certain changes that I do here, right? So it's not that it doesn't carry info, it carries information. How am I going to run my diffusions, and how is my poly going to run? Where am I going to have the inputs? Where am I going to have the outputs? It carries some valuable information about how the structure of the layout will look like. The dimensional information, once I, sort of sketch the structure of the layout, the dimensional information, then I'll go ahead and add later. Okay. So in any case, even if you don't want to do a stick layout, let's say if I give you a circuit and you have to construct a layout of this, it's a good idea first to sketch a stick layout. How am I going to organize my layout? Where am I N plus going to be? Where am I P plus going to be? Where am I poly going to be? And how is the poly going to run? Where are the contacts going to be? You know, very quickly you can sketch this. And once you can sketch this, then of course, sit down, look at all the rules and expand them and construct the final layout here. So if you're constructing a layout manually, this is a useful representation, but it will become even better representation if one could do the following. If let's say a designer, you know, he has to construct a layout like this. So let's say if a designer constructs this, you know, draws a stick layout, and you know, you can see here, you can compare the effort required to draw this versus the effort required to draw this. There's a huge effort. Yeah, right? Or to do this particular one. I mean, difference in the effort. So a person sits down and draws a stick layout, very quickly sketches, right? So he has this intermediate format. Now I have to add technology information and to arrive at this final layout. And note that the second step is not a very creative step. The creative step is this one, where I decide how am I going to arrange the different things. That's the creative step in a layout. The second step is very routine. Just look at all the rules and expand it and you know, connect them up. So if I can write a CAD tool here, if I can write a CAD tool which will take your stick layout, add all the technology information and produce the final layout, that would be very nice. So all that you need to do is you do the creative part, right? Decide how the layout is going to look like, where are you going to place N and P and all of those things. You do the creative part that is there here, which is rather, I mean, not too difficult. So you're not burdened by all the rules that are there here. So you do the creative part, and the routine part and the mechanical part, you leave it to a CAD tool, which will do that for you. Right? So that's the design philosophy that one is talking about. Right? Instead of sitting down and doing the whole layout all by yourself. And don't look at this intermediate step. So whatever circuit is given, you jump straight to this particular part here. Right? And if you try to jump to this particular part, maybe some of the, you know, your thinking will be, as I said, will be burdened by all the rules, information and all that. So this full layout stage where you're sort of sketching the stick layout will help you in your ability to come up with different ideas. So even if, let's say, there's no CAD tool and all that is there, you still have to do it. This stage, intermediate stage, will help you conceptualize your layout better. And then you go ahead and do it. Okay. So stick layouts and all that have that particular advantage. All right. We've looked at how we can construct NMOS here and a PMOS here, and how we can connect them up with metal and all that. So many circuits have, most of the digital circuits have NMOS and PMOS, but there are places where we sometimes do require a resistor, we do require a capacitor, and especially in mixed signal circuits where you have digital and analog both. In analog, you may require resistors and capacitors, but you may even may require at places, especially when you go to very high frequencies, you may require an inductor, and you may even require a transformer. Can we do these things on an IC or not? So a very quick and very limited discussion. Let's go through that. So resistors, how do we make resistors? Right, so we know how to construct a transistor, NMOS and PMOS. How do we make a resistor? So I've shown you, the typical CMOS process which is constructed, the process which is there, has been designed to make transistors. Has not been designed to make a resistor or a capacitor or an inductor. The whole process is organized to make NMOS and PMOS. Now you look at the process and see, can I use something here? You see various things that are there in PMOS. What do I have? Or in NMOS. What do I have? I have a substrate which is available. I have an N well available. I have these P plus regions available. I have N plus available here. I have a poly which is also there conducting. I have all these layers, and I have metal 1, metal 2, all these layers that are available to me. Can I use this to make a resistor of a certain value? So now when you make a resistor, all of you know this, R equal to rho L by A. And normally when we talk about resistors, we don't talk in terms of resistivity, but what we do is area, you take the width out and the thickness. So the resistivity divided by thickness is what we call as sheet resistance. So you have these different layers that are available. I can maybe use an N plus layer to make a resistor. N plus layer is there. It will have a certain sheet resistance, and I can make two contacts to my N plus layer, and I have a resistor. Is it a good resistor? Is it a bad resistor? What kind of a resistor do I get here? So note that we'll think of a resistor as a sheet resistance. So sheet resistance values of these different layers are given. Sheet resistance of all these different layers are given. These are available as part of the technology. And L by W, of course, you choose as a designer. How long do you want and how wide do you want here? For example, look at this technology information. This is for a 0.5 micron technology. So for example, the manufacturer would give you this. That N plus active layer that I just talked about, this N plus layer, it says its sheet resistance is 2.8 ohms per square. Note that sheet resistance, go back again. Resistance is ohms, L by W, unitless, right? Okay. So ohms, 2.8 ohms per square. So if you make a square, L by W is 1, L is 1 and W is 1, so you get 2.8 ohms. That's N plus. P plus is 2.3. Poly is 2.4. And metal 1, obviously, sheet resistance is very small, 0.07. Metal 2 is 0.07. Metal 3 is 0.05. Poly with a silicide block, let's not worry about it, is 113.5. There's an N well which is 726 ohms per square. So the manufacturer is giving you the sheet resistance of different layers that are there. All right. So for example, I can take a sheet resistance of N plus region is 2.8 ohms per square. That's the sheet resistance of N plus region. Let's try and make a resistor. Remember one of the examples that we were looking at, we wanted a resistor of 100K, 80K or 100K. So if I put 100K here, R equal to 100K, sheet resistance is 2.8 ohms, L by W comes out to be 3.5 into 10 power 4. How will I make this resistor? Well, let's say I use a W of 4 micron, width of 4 micron, L will become 10 to the power 4 micron here. 10 to the power 4 micron will become a centimeter. Okay. How would you make this? Look at this. This is the N plus region here. So you'll make N plus region here. You'll make a contact here. You'll make a contact here. That will become a resistor. First of all, we'll come to that. The aspect ratio is very odd. 1 centimeter long and 4 micron thin is a very odd kind of a layout. But we'll come to that. But right now, look at the area. The area of this 100K resistor is 3.5. So if you use a width of 1, let's say, so area is 3.5 into 10 power 4 micron square. Okay. 3.5 into 10 power, so 10 power 4 microns is this thing here and 4 here, so area is here. In contrast, we had seen, if you go back and look at the NMOS area is only 4 micron square. So note that in this technology, CMOS technology that we are talking about, a 2 by 1 NMOS costs you only 4 micron square. A 100K resistor is, look at the size. Huge. So this is one of the reasons why in this entire MOS technology, we try to avoid resistors. Don't use resistors. They're too costly. They're too big. And we'll see that they're not very good also. All right. So this is 10 to the power this thing here. So just because I used an N plus, we'll try and use other regions also. But the other point is, note that this has a very odd aspect ratio. So we won't make it like this. We won't make it like this. Typical way that you would make it is like this, in a serpentine form. Serpentine form, then the aspect ratio becomes better. It's no longer a thin, long sort of a wire. It's more, you can make it more squarish here. Even this, note that as the current starts from here, it flows here, and at the corner there are usually problems. It's difficult to model how much is the resistance at the corners and all that. So many times what happens is, when you do a resistor, you make a metal contact here also. So what happens is, the metal and the contacts have very little resistance. So you have a resistance of this N plus here, then you have almost like a short, then this N plus here, and then you have a short, and then like this. Right? So you construct a resistor in this serpentine form. And you decide how long do you want it to be and how many fingers do you want it to be. And the idea is you have to look at where are you going to place this resistor, how much space do you have, and on that basis you decide what should be the aspect ratio, the height versus the width of the resistor here. So you would make it something in this form, rather than a long and thin kind of a thing. All right. So the other point is these resistors are, as I said, they are not very good. They have a temperature coefficient, fairly significant temperature coefficient. We all know resistors vary with temperature, and temperature coefficient of this one is, note that if I use an N plus P plus layer, temperature coefficient is 1500 parts per million per degree Celsius. 1500 parts per million means 1500 multiplied by 10 to the power minus 6. So 1500 multiplied by 10 per minus 6. So we are talking about 1.5 into 10 per minus 3, right, per degree Celsius. So 1 degree change in temperature will cause a 1.5 into 10 per minus 3 change in the resistance here. So as an example, our resistor value may change by 27% for a change in temperature from minus 55 to 125 degrees. It will change by that much. Minus 55 watt, maybe deep winter somewhere in Arctic. 125, well, normal ambient temperature doesn't go to 125, but the chip temperatures do go high. When you have an IC and you're consuming a lot of power, the chip temperature may go up to 90 and 100 degrees Celsius. Okay, so these temperatures are, don't think that this is totally unrealistic. So it has a temperature coefficient, and significant change in resistor value may occur. The other one is the resistor that I just constructed, its value depends on voltage. That's another bad aspect of it. Note that in this case, I'm showing a P plus region here. So note that P plus, I have a P plus region available in an N well. So I have an N well here, and in that I have a P plus region here, and I make two contacts here. And so this becomes a resistor. Now, what happens is when you have a P plus and you have an N, you have a depletion region. You have a depletion region, and there's N well has much less doping compared to P plus. So most of the depletion region is in the N well. But there's a little bit of depletion region here also in P plus. As you change the bias applied to it, the depletion width change. And as the depletion width change, the effective thickness of the P plus layer changes. And then the resistor then value changes with the voltage. Okay. And so this is also measured in terms of voltage coefficient. If I change the voltage, how much does my resistor change here? So anyway, I don't want to spend too much time, so it has a certain voltage coefficient. The other one is, it's not a pure resistor also. Note that I just said that it's a resistor here and there's a depletion region. Now when there's a depletion region, there's a capacitance. So even when you're making a resistor, as a bonus, you get a capacitor also, right? You don't want it, but you're getting all these capacitors, right? So it's not a pure resistor. From here to here, I get a resistance, fine, but from here to here, there's a capacitance. PN junction is there. So I get a capacitance. So it's not an R, pure R, so this is what the other problem is. And the capacitance may be significant for certain cases here. So as I said, I'm not going to go too much into it. There are other ways of implementing a resistor. So we just talked about N plus and P plus. I could also use a poly. Note that polysilicon is also doped. So I can make two contacts on the poly and use that as a resistor. And a poly will have its own values, sheet resistance, temperature coefficient, voltage coefficient, and you can evaluate how good that particular layer is for making a resistor here. More interesting is that use the N well. If you want a high value of resistor, the N well has available to you the highest sheet resistance. The sheet resistance of N well is 726 ohms per square, as compared to 2.5 and 2.8 for N plus and P plus. Those sheet resistances were very small, and that's why we had to use a large size to obtain the resistor here. This sheet resistance is high, 726. But it has this, note that temperature coefficient is high. Voltage coefficient is also very high, very sensitive to voltage. It has a capacitance associated with it. Let's look at this one here. So use the N well, make a N plus contact and an N plus contact, and put a metal contact on top, and in between you get a resistor. Okay, and so for example, if I were to make, I've left that as a homework problem for you to figure this out. So suppose I'm making an inverter. Very simple inverter would be an NMOS, let's say with an 80K resistor. So this 80K resistor, if I try and implement using this N well, and N well sheet resistance is given to us, so I end up getting L by W is 110. Still is large. L by W is 110. you can compare so once you do the layout, you will see what is the size of the MOSFET and what is the size of the resistor that you get here. And you'll see why I don't want to make a inverter with the resistor there. With all the other problems that are there with the resistor, its temperature will change. I mean, with temperature, its value will change. It has a capacitance associated with it and all those other things that are there. All right, so there are other things. So let's come to capacitors. So we see we don't have very good resistors available to us. Okay, capacitors. How do I implement capacitors here? So capacitors again take up fairly large area, and you cannot make capacitors except in picofarads. Even nanofarad capacitors are not possible for you. You can do the calculations yourself and come up with the numbers and see why it is unrealistic. So one way in which you can make a capacitor is as follows. Look at this particular layout here. So what we have used is, you have a normal silicon substrate which is p-type. I can create an N plus region here, make a contact to this N plus here, and make a contact to the p-type here, which is p plus here. Right? How is it a capacitance? How is it a capacitance? Contact to the N plus and contact to the P. Where is the capacitance coming from? N plus P, depletion region. It's a PN junction which is kept reverse biased, and you have a PN junction here, and you get a capacitance in between. Right? There's one problem with this. Note that this is the, if you use it like this, the P-type substrate always has to be connected to the most negative point. Right? So this end is fixed. You don't have a choice of what you can do with this. This end is fixed to the ground. Let's say if the most negative point is the ground, so this end is connected to ground. You don't have a floating capacitor. Both ends are not available to you in this case. This is how you may do a layout of this. So you, depending on the the capacitance here value, you construct a particular area. You make one contact. You see this contact here, and there's another contact which is the other contact to this one, and you construct a capacitor.
Sir,
yes.
So P plus and P.
This one, yes. You make a contact to the P plus here. So you have to create a P plus region to make a contact to the body. The body is here. So this is, you can also use, don't use the N plus P, but you can use the P plus N. The P plus is also available in the N well. So use that layer to construct the capacitor also. So you can use that as well. I think that this is what it shows here, the upper one. So there is an N well, and you create a P plus region here, make a contact here, and make a contact to this. In this case, both the terminals are available to you. You can apply any voltage here, any voltage here. Right? So note that you have to construct a well, and then within the well, this is the P plus region here, make a contact here, make a contact to the body, and you have a capacitor. And what is the value of the capacitor? Well, I've given you some values earlier. If we go back, note that this picture here for 0.5 micron, they're telling you what kind of capacitances we get. So it says if you're using a P plus layer, between the P plus layer and the substrate, the capacitance value is 930 AF. AF is what? Pico, and then femto, and then atto, right? 10 to the power minus 18 farads per micron square, right? So this is the value that is available if you're using an N plus or active layer. So between the N plus and the substrate, so we were saying use the N plus and the substrate. The capacitance value is 477 AF per micron square. So now you calculate, try and make a 1 nanofarad capacitor. Find out how large an area you will get. Okay. All right. So try and do that and see how much area you require. So all the technology information. So please take a look at this. This one here is telling you what are the capacitors available between different layers. All right. So try and use that to construct the capacitors here. So you can use again N plus layer here or P plus. Another way that you can use is try and use the MOSFET itself. So suppose I take the source and the drain, I short it together, that becomes one terminal, and I use the other terminal. Now, why is this interesting? Because note that between the gate and the channel, there's a very thin oxide. It's a very thin oxide, so capacitance per unit area is fairly large. So if you want a large capacitance, this gives you a good way of doing that here, right? So so this is one terminal here, which is the gate here, and these two are shorted together. So this is the other one, right? The difficulty with this approach is, note that you will get a high capacitance only if you get a channel here. If there's no channel, then there's no communication between this and this layer here. So you need to create a channel, which means that this capacitor will only work if the voltage is above threshold. If the voltage is above threshold and there is a channel, then you get a capacitance between them. But if it is not, then you have a problem. So in a way, the capacitance is voltage dependent. If you are above a certain value, then it's fine. So this is how you may do a layout of this particular capacitor here. This is all taken from the simulator that I told you, microwind. So they have these examples here. So these are note that this is if you go back, these are the two N plus regions here, which are shorted together. So they have here and here two contacts shorted together. And the poly, this is the contact to the poly here. This is the upper contact here, this one. That's how you make the capacitor here. Well, you can take a cut line and you can see how things are connected together. You can take a cut line here. Now let me not spend time here. There's another way of constructing the capacitor here, where what you do is you take N plus. Some processes may allow you to create under the gate a N plus region here. In the normal process, under the gate you have a normal P silicon. But some processes may allow you to create under the poly a N plus region here. So note that if I have an N plus, N plus, N plus here, I don't need to create a channel anymore. In the previous case, I had to apply a voltage, create a channel, then only I get a capacitor. Now there is an N plus layer here. So this forms one plate and this forms the other plate. And now you get a much better capacitance than in the previous case. Let me skip this. There is another layer. There are different layers of metal. This is metal 1, metal 2, metal 3, metal 4. So you could use and between two layers of metal, there is a dielectric. So I could take these and short them together, and these ones here, and I can try and construct a capacitor using this. The only problem is that the oxide in between is pretty thick. It's fairly thick, which means that the capacitance per unit area is small. Note that 0.041 femtofarad per micron square. So capacitance is, and if you want to construct a capacitor, it will end up taking a lot more area. So that's the problem. So capacitors are again a little bit difficult, and therefore in some of the processes, what the manufacturers do is normal processes have one poly layer. What they do is they give you another poly layer. So there are processes, you have to go and look for those technologies. They will offer you two poly. And this two poly that you see here, this is a normal polysilicon, which is for making transistors. They will offer you another poly, and in between the two polys, there is a very thin oxide. And so you can use these for forming capacitors here. Note that one poly is here, another poly is here, and the polysilicon, as I said, these are doped, and so they are conducting. So this forms one plate, this forms another plate, and in between is a fairly thin oxide. So one of the best ways of making a capacitor on chip is to use these two poly layers here. And then you make the capacitor, let's say. Well, inductor. For an inductor, all you need is a spiral, right? So we have a metal layer, and all that you do is make a spiral, right? And you get an inductance. So I can use this. So let me show you. You can make inductance, but you don't have a iron core and things like that, so you don't get large values here. The problem with the inductor is that its Q factor is pretty low. Now try to recollect inductor. A pure inductor, any inductor will come with what? Parasitics and resistors. And it may also come with capacitances. It may come with capacitance, because note, if I'm using a metal one to make a spiral, where is this metal one sitting? On top of silicon dioxide. And underneath the silicon dioxide is what? Substrate. So I have a capacitance. I have a capacitance associated with it. So that's a major problem. I don't get a pure L. Along with it, I get parasitic capacitances here. And so note that the quality factor that I get for an inductor, so we are talking about inductor 3.5 turns, R equal to 60. Do we see a value of the inductor here? Inductor would be in somewhere in nanofarads. It's not, it's okay. So note what they're showing is, so just look at the quality factor. This is 1 gigahertz. So if you are 0.1 gigahertz, 100 megahertz, the quality factor is less than 1. Q is less than 1. Now, it's obvious that as I go to higher frequencies, why the quality factor is improving, omega L. Omega times L, so as omega increases, the quality factor increases, but then there are capacitors also. So you note that this is taken from a paper. They show these parasitic resistances and they show all these capacitors that are there. So it's not a very good inductor, but you can at certain frequencies that you see here, especially higher ones, you can get maybe at 1 gigahertz or so. In this case, you get a quality factor of 4 or 5. So you can make inductors. Well, you can make transformers also. You can make transformers also. Look at this one. You can see 2 coils, right? One coil starting from here and the other coil secondary. Right? So primary and secondary, both are there. So you make both of these on top of using metal 1 or metal 2 or whatever. Use these to make a transformer. So where do I need transformers, especially when I go and do RF circuits? So this is an example of an RF circuit that you see here with a lot of transformers here. You can see a T3 here and a T1 transformer here, and what else? Do we see another transformer? T2. You see 3 transformers. In this circuit, they require 3 transformers. And this is the layout of their amplifier. You see 1 transformer here, 1 transformer here, and 1 transformer here. 3 transformers. And plus other things, transistors and all that would be there. So yes, you can make an inductor, a very poor inductor. You can make a transformer, not a very good transformer, but still, as you go to higher frequencies, still it performs a useful function and you can do these things. Okay. So the MOS technology is best suited for what? Best suited for making an NMOS and a PMOS. That's it. Resistors are not very good. Capacitors only of small value. Inductors also of not a very good quality. Literally, quality factor is poor. You can make transformers. You can get some complete coefficients. But realize that for many of these things, the fact that you can make it is, otherwise, what are the alternatives? Think about what these people have been able to do, make a complete amplifier here, which requires transformers. If they're not used on-chip transformers, what is the alternative? You have a chip here, and then you have to construct an external transformer, right? 3 of them. And you can imagine the external transformers, their weight, their size, and how unwieldy it will become. So even the other solution is not a very attractive solution. A transformer there, a physical transformer, big one sitting outside. So even that is not a good solution. And as I said, as you go to higher frequencies, the inductive effects become stronger. Inductive effect depends on omega and L. So inductive effects become stronger. And if you can minimize the parasitics, then you can get reasonable values here. Before I leave this particular topic, just a couple of tips when you are doing layout. One of them I've already talked about, that use multiple contacts. You want to minimize the resistance. Note that this N plus and P plus regions have resistances. You want to minimize the contacts. You want to minimize the resistance. Use as many contacts as possible. So that's one. The other one is, many times, for example, you may find a transistor which is 20 by 1 or 200 by 1. Don't make a transistor like this. A long and thin transistor like this here. You can make transistors like this with multiple fingers. So this is source and drain and source, and you can have multiple fingers that are there, which is effectively constructing things in parallel. So if you have 200 by 1, you may require at certain places a transistor which is 200 by 1. You make it by putting maybe 10 transistors, each one of them 20 by 1 in parallel, or 20 transistors, each one of them in parallel in 10 by 1. Note that you can see also there's a savings also. If I make it like this, my source area or a drain area is of this area, this dimension. Here note that this area that I've put here is shared between the two. The drain acts as a drain for this one and also acts as a drain for this one. So there is a savings in area, and remember, savings in area is not just a geometrical, physical saving in area. Any area that you save also translates into capacitance. The capacitances are also minimized. So when you have a large aspect ratio, don't draw it as a long, thin one. Try to use multiple fingers, okay, to get this one here. At various places, not so much in digital. This you can see here. This is a differential pair. A differential pair is like this, or you may require a current mirror. Where what is important is that the two transistors should be very well matched. The matching between the two transistors is very important. Now, even though I have a process and let's say both the transistors are being manufactured at the same time, the two transistors are not going to have the same VT. Threshold voltage will not have the same mobility. Things will vary. One doesn't have that much control over the process that each one of them has precisely the same threshold voltage. And any mismatch in the threshold voltage, all of you in 380, did you measure the offset voltage of an op-amp? Right? Offset voltage of an op-amp, where does it come from? Well, one of the things is the threshold voltage mismatch. Threshold voltage mismatch between, you were doing with bipolar, but if you do it with a MOS, the threshold voltage mismatch is a major source of the offset voltage in an op-amp. Threshold voltage mismatch, mobility mismatch, and things like that. Now the issue is, if I want to minimize the mismatch, what I should try and do is, the mismatch between two transistors depends on, one of the things is how far they are. Pretty obvious. If two things are very close to each other, it's likely that the processing conditions are similar for both of them. If you make it far away, then the processing condition here and processing condition here may be a little different, and therefore the threshold voltages are different. So one of the things is, if you want very good matching between the transistors, make the two transistors very close to each other. So in this case, is this the best that I can do? Or can I bring them closer? Well, you'll say, okay, bring the physical distance closer, so I can bring them as close as my design rule allows, right? I can do that as close as possible to the design rule. Or I can do a layout in a different way, which minimizes the distance between the two transistors. Well, let me show you one solution here. What if I do like this? I don't make them two transistors physically. Note that the source is also shared between them. So I do here. Source is here, D1 is here, and D2 is here. Is there a distance between the two MOSFETs? How would you, if I have to talk about the distance between two MOSFETs, how would I do that? You're clearly seeing one transistor is here and the other transistor is here, right? There is a distance between them. Can I make two transistors such that the distance between them is zero? Zero distance between them. Two transistors with an effective distance between them, zero. Sources are connected here. Source is common. But note that this transistor is on the top, this transistor is at the bottom. There is a separation. And why am I talking about this separation is problem? Note that what if there is on my wafer, what if there is a temperature gradient like this? When I'm processing, I'm heating it up and in an oven and all that. And what if there's a temperature gradient like this? At higher temperature here and lower here. So if there is a temperature gradient, then what would happen is maybe the oxide thicknesses are different, or the dopings are different and all that. So doping may be a little bit different here, doping may be a little bit different here, which will translate into differences in threshold and mobility. I want the separation between the two transistors to be zero for the best matching of the two transistors. How can I do that? Is it possible? Look at this one. I use the word effective separation between the two transistors is zero. Both the transistors have the common centroid. Centroid of the two transistors is the same. You see, I've created a symmetry. Whatever happens, let's say if something happens here, the same thing here. So what we are saying is the following. I take my transistor M1 and I split it into branches here. One part here, one part here. And so the centroid of this one is here and the centroid of this one is also here. So when we construct a layout, what we are talking about is both transistors have the same common centroid. Try to split a transistor into multiple parts and try to make the centroid of the transistors common. Right? So, break it up into so that if something happens to one part here, the same thing happens to the other part. Right? So, for example, one could break a transistor into M1, M2, M2, M1 and all that like this here. Right? The chances are that when you measure the threshold voltage mismatch between M1 and M2, now you will find that the mismatch is much smaller as compared to completely making M1 at one place, completely making M2 at other place. Okay, so this is a very common technique where the transistor is split into fingers and is constructed in the form of a common centroid. So all for differential amplifiers and for current mirrors and things like that, matching is improved by constructing in this. Of course, I have not shown here this D1 will have to be connected to this D1 here, this D2 will have to be connected here, G1 will have to be connected here, gates have to be connected together. So I've not shown the connections between them. Okay. So what I'm trying to say is that you can effectively try to minimize the separation between the two transistors by splitting a transistor into multiple fingers and trying to achieve a common centroid.